Hi girls, right, so we're back now with hinges. So I'm going to take the first one, first example on your handout, number 6. It's very similar to what we've been doing now in the last section with ladders. We're just going to continue it on a little bit and extend it. So, reading this question, it says, a uniform rod, AB, here it is, its length is 2 meters and its weight is 40√3, is freely hinged at end A to a vertical wall. Okay, so this word hinged, this is what we're going to focus on. It's hinged. One end of a light inelastic string is attached at B, and the other end of the string is attached to another vertical wall as shown in the diagram. So here's our rod, this is the string here. The rod makes an angle of 60 degrees with one wall, and the string makes an angle of 30 degrees with the other wall. The rod is in equilibrium. You've got to show on a diagram all the forces acting on the rod AB. Okay, so let's draw that diagram first. So what do we have? We have 2 walls, and we have this rod AB, and then we have a piece of string attaching that rod to this wall over here. So I'll put that piece of string in red. Okay, now the question says that this rod AB is freely hinged at position A. So this is very important here. So I'm going to circle that to make sure I pay attention. I always put a circle on where the hinge is so that I remember what I'm going to do as the question proceeds. Right, this is at 60 degrees. This is at 30 degrees. Right, show on a diagram all the forces acting on it. Okay, so this is your starting diagram. This here is 90 degrees, it says, so that's at a right angle. And this is, as it says, that piece of string. So we're just looking for the forces acting on the rod. So let's take the rod out of that diagram here. So here's my rod. And I'm going to show all the forces acting on it. Of course, it has a weight force, which always acts down through the middle of the rod, down towards the centre of the earth. And that weight, I'm told, is 40√3. This string is acting in this direction. So this piece of string is going to offer a tension. I'm going to call that tension force T. Now, the other things I'm interested in is this fella over here, this A, the hinge. The hinge reaction is made up of 2 components. It's made up of a vertical component and a horizontal component. And just as we go through the question, I always put the 2 components, so the vertical one and the horizontal one, I always put them in those directions. So say positive y-axis, positive x-axis, and it doesn't matter, because as you're going through the question, the signs of the forces will sort themselves out, and you'll actually see which way they're acting. Okay, so but just start off, put them in the positive direction. Now this, I'm going to call it the x component, and this is the y component of the hinge. Okay, so they're my forces. That's my force diagram. Now, it says, write down the 2 equations that arise from resolving the forces horizontally and vertically. Okay, so this is a horizontal and a vertical force. This is a vertical force, but this isn't. So I've got a bit of work to do. So I'm going to have to now draw a diagram resolving the forces. So I'm going to resolve the forces so that I can use those, use the diagram. Okay, so here again, this is 40√3. This is my force diagram. This is x component. This is the y component. The T. Okay, so here's my T force. I'm going to draw a right angle triangle around my T force. So I'm going to here, actually I'll draw it there, and across like that here. And the reason I'm just doing it that side is because I've got a nice angle to help me up here. So this angle here, remember, is 30 degrees, which means that by the alternate rule, this is also 30 degrees, or I could look at it that that's 60. Okay, so I'll say this is 30 down here. Okay, so now I'm going to label these two components of that T force. So this one here is, of course, opposite the 30 degrees. So this will become T sine 30. And this one is adjacent, so that one will become T cos 30. Okay, so I'm breaking them up so that I can use them. Now, once I've done that, remember, I no longer want this T now. This is gone because I've broken it up into its two components. So don't forget to cross it out. Okay, right then. So that's my forces resolved so that I can now do the second part of the question, or the third part of the question, which says, or second part, write down two equations that arise from resolving the forces horizontally and vertically. So we're going to assume that this rod is in equilibrium, and if it's in equilibrium, then the up and down forces have to be equal and the left and right forces have to be equal. So the up and down, there's a y force is up, and I've got a T cos 30, that's also acting in an upward direction. They must be equal to the downward forces. There's only one, 40 root 3. So that's one equation. Now, the horizontal resolving results in the left equals the right. So I've got a left, which is x, and I've got another left plus T sine 30. There isn't any right forces, and that's going to be equal to 0. So at this stage now I can see that if I brought that T sine 30 over, this would become x equals minus T sine 30. Remember, these are all forces, so they're magnitudes, and the signs in front of them are the directional signs. So really this sentence is telling me that the x doesn't act in towards the right or coming in this direction. It actually acts towards the left. It's not going to make any difference as we go on through the question. Okay, so that's the first two equations. Now it says, write down the equation that arises from taking the moments about point A. Okay, so we're going to use the law of the lever now to do this part. In order to do the law of the lever, remember, I've got to say that the anti-clockwise moments equal the clockwise moments. And to get a moment, I'm going to need a distance for each force. So an anti-clockwise moment equals the clockwise moment. So I'm now going to do a distance diagram. So now we're going to do a distance diagram. Right then, so we've got the wall, two walls. We've got this rod, remember, AB, and we've got this tension in the string. Okay, now then, the forces we're interested in are the X and Y forces, which are passing right through the fulcrum. So therefore, at the moment, their effect is going to be 0. Now, this is my weight force. Weight of the rod is 40 root 3. Okay, look how far it is from the fulcrum. It's from there to there. So that distance from there to there, what will it be? Okay, this angle here, remember, is 60. This acts halfway along the rod, so that distance there is 1. So this little bit here is going to be 1 sine 60. Okay. Now, the next force that I'm interested in is the T cos 30 force. Here it is. It's going right down from there to there. Its distance from the fulcrum is from there to there, which of course is from here to here. So this is the bit I'm after, that bit. So it's the entire length of the rod, which is 2, and again that's 60, so this will be 2 sine 60 for that bit. Okay, the next one I'm interested in is this one here, which of course is t sine 30. So this is my t sine 30 line of action. How far is that from the fulcrum? Well, there's this line of action, which means it's that distance from there to there from the fulcrum. And that is the entire length, so it's that large triangle here. So this is 2, and it's the adjacent side to the angle. So this bit here will be 2 cos 60. Okay, so they now are my distances. Now remember, the question asks me, write down the equations that arise from taking moments about the point A. Right, so let's do this, moments about A. So the anti-clockwise moments must be equal to the clockwise moments. So if I was to move that rod, here's the rod, there's the fulcrum. So if I was to move that rod in an upward direction, what forces would make it move up? So that would be up forces coming from the left. And if I was to move it in a downward direction, that would be down forces coming from the right. Okay, so I have a look at my up forces and my down forces. Okay, so back to this diagram, back to the last diagram, the last page. The up forces are t cos 30, t y, and from the left is x and t sine 30. So they're all the forces up from the left. The down forces from the right, that's just the 40 root 3 force. Okay, let's put the distances of each force now from the fulcrum, and then we'll be able to work out the moments. So the t cos 30 is twice sine 60 away. Twice sine 60. And the t sine 30 is twice cos 60 away. That's this one here. Twice cos 60. The x and the y, of course, are going right through the fulcrum, so they're going to be 0. The 40 root 3 is 1 sine 60 away. Okay, so now if I write down an equation, sort this out, it becomes 2t cos 30 sine 60 plus 2t sine 30 cos 60 equals 40 root 3 sine 60. And when I put in all those values, this becomes 2t cos 30 is root 3 over 2. The sine of 60 is root 3 over 2. Plus 2t, the sine of 30 is a half, and the cos of 60 is a half. And that's equal to 40 root 3 by the sine of 60, which of course is root 3 over 2. Now when I work all this out here, the root 3 and the root 3 will become 3. So this will become 3t. One of those 2's will cancel with that. So this will be 3t over 2. That will cancel with that, and that will just be a half t. Equals 3 root 3 by root 3 is 3. 2 into 40 goes 20 times. That will give me 60. So that's going to be 2t is equal to 60. So t is equal to 30. And of course it's a force, so it's in newtons. Okay, so we found the tension in the string. Now the last part says find the magnitude of the reaction at the point A. And we're also going to find the direction. It doesn't ask me to do this in the diagram, but in the question, but sometimes it does, so we're going to do it. So we're going to look for the magnitude and direction of the reaction at the point A. Right, so at the point A, of course, so this is my, this is the point A, we'll say, along the rod. The forces that we have, that hinge force, is made up of two components, X and Y. That X and Y component now is what I'm looking for. So I want to find the reaction. And if you recall, when we were looking at this X, when we were putting it in at the first part of the question up here, when we were putting up, downs and left, right, we had this fella here, that x plus t sine 30 is equal to 0. So x is equal to minus t sine 30. So of course, if it's minus t sine 30, what it actually is doing is going in that direction, isn't it? But that's just a directional thing. It's not going to have any effect on the magnitude. So let's find x and y so that we can get the resultant. Okay, so what we have is force x, force y. If I were to move this force over here, and this is where I started and that's where I finished, this is the one I'm interested in. This is the resultant. So that's what I really want to find. So that's my y. That's the x. So this is the triangle I have. Y, x, resultant. And of course I solve that by getting Pythagoras. So the resultant is going to be the square root of x squared plus y squared. And I use Pythagoras. So my job now is to find x and y and fill it into this equation. Okay, so if I go back again to these up and down, up equals down and left equals right, because the rod is in equilibrium, I have these two equations with x and y. So I'm going to use them to give me a value for x and a value for y. Right then, so x plus t sine 30 is equal to 0, which means that x is equal to minus t sine 30. T we said was 30. The sine 30 is a half, so x equals minus 15. That's if it's going in that direction, so that just means that x has a magnitude of 15 newtons because it's coming in this direction. Okay, the other equation was that y plus t cos 30 is equal to 40 root 3. So when I fill what my necessary parts in here, t's 30, cos of 30 is root 3 over 2, 40 root 3. This will give me 15, so y plus 15 root 3 is equal to 40 root 3, and when I bring this over, this gives me 25 root 3. So now I have x and y. So that means my resultant is the square root of 15 squared plus 25 root 3, all to be squared. And when I pop that into the calculator, I get a resultant of 45.826 newtons. Now the last part that I'm going to do, which isn't in the question, but we often do have to do it, is to find the direction of that force, the direction of the hinge force. Okay, so here it is. Here's my resultant. So let's get a direction for it. So there's my resultant force here. I'm going to nominate an angle here called x. This is y, that is the x force, which means to describe this angle x, the tan of alpha is equal to y over x. So I'd always really find the direction as with respect to the y-axis or the x-axis. So that means that in this particular case, alpha is equal to arc tan y, which is 25 root 3, over x, which is 15. So when you work that out, you get 70.89 degrees. Okay.